Hi, welcome to the Signal Path. In this episode, we're going to continue our review of the Siglent SNA5014A, which is a 4-port 8.5 GHz network analyzer. These units now go up to 26.5 GHz, which is fantastic. Siglent continues to expand their RF equipment portfolio. In fact, I've been so happy with this that I bought one for work that we use around the lab. Now, if you remember, when I reviewed this, the instrument had just come out, and we did a complete teardown and analysis of exactly how it is built. And we found that port 1, port 2, and port 3 and port 4 use different RF acquisition and synthesizer boards. Now, once you have sufficient number of synthesizers between all the ports of a network analyzer, you can begin to do some really interesting measurements. In fact, you can do nonlinear measurements, mixer measurements, because you have enough synthesizers to down-convert across different frequencies. And if you have pulse generation and detection capability, you can do TDR measurements as well and create eye diagrams of various channels. So the capability of this instrument now depends a lot on software development. And Siglent has indeed continued to develop a variety of softwares for it, and I want to take a look at some of those interesting applications. I don't even have all of them because they developed so fast that I don't have all the licenses, but some of the key ones I think we have, and we can get an idea of what this can do in a real-world scenario. So let's take a look. So let's consider a situation where I want to measure the conversion characteristics of a mixer. A mixer is going to have an RF port, an LO port, and an IF port. Now, in a normal network analyzer, where you don't have sufficient independent sources, you really can't do this measurement directly only using the network analyzer. That's because the RF and LO source inside the network analyzer are going to be so tightly coupled in frequency in order to create the IF required for making S parameters. But if I have an independent source, now I can tune that independent source anywhere I want and therefore move these frequencies with respect to each other in a much more free way, allowing me to actually measure conversion characteristic. In fact, there is a license for this instrument that allows you to make the vector measurement of that too. We'll talk about that in a second. So the beauty of this software option is that you just have to use the network analyzer directly connected to the mixer and get its characteristic, which I want to try out. Now, before I can do any mixer measurements, I have to configure the instrument correctly for that type of analysis. We are looking at the remote display of the Siglent network analyzer, which comes up really easily by connecting it to an Ethernet port and then typing in the IP address. Some of the other vendors should take note of how well Siglent has handled the remote display into the instrument. It's very seamless and very fast. Now, in order to change this into a mixer measurement, we just have to simply go under the measurement menu over here. And if I go under mode, you can see that we're in a basic VNA mode. Of course, that's the primary function of the instrument, but there are several other ones like spectrum analyzer, material measurements, and we're looking at the scalar mixer measurement. Notice how there are two new additions after the firmware update. I don't have the license for them yet. One is a vector mixer measurement, which is very interesting too, and gain compression. I'll talk about those a little bit as well. Let's go ahead and select that. It's going to replace our existing measurement. And now in this window, we have a comprehensive set of options to configure the instrument for a wide range of frequency conversion techniques and measurements. So let's take a look at the sweep types here. We have, of course, linear frequency sweep. These sweeps are the same as the sweeps offered by a network analyzer. Segmented sweep is interesting for mixers because you may not want to always look at every possible frequency up and down conversion. You can create this for faster sweeping. Power sweep is critical for mixers because mixers often have a conversion range which are a function of the input power, which we will take a look at. For now, let's keep the IF bandwidth at 10 kilohertz. Let's give it a few more points, 1,000 points. Now, there are 3 tabs up here. I think it makes sense to start from the mixer tab. I think they need to change the order of these for it to be more logical. Now, under this window, we can configure the relationship between the network analyzer and the mixer device under test. Here, I have defined port 1 to be connected to the input of the mixer, port 2 to the output of the mixer. Now, it doesn't matter if this mixer is down conversion or up conversion. We're just simply defining the port connections. The frequency range and frequency planning comes next. Now, of course, every mixer is a 3-terminal device. It's going to require an LO input. We can configure the instrument to use an external LO, an external synthesizer controlled by the network analyzer. But we know that this is a 4-port network analyzer with independent synthesizers inside. So I can just simply ask it, use port 3 and apply the LO from your own internal synthesizer. And that means that now everything is handled by one unit. And as soon as I do that, I now have control over the port 3 power, which is very important because LO port power is critical for getting the correct conversion gain from a mixer. Now, this mixer requires a 10 dBm LO power, which this instrument has no problem applying. Now, you also must have noticed that there are these ratios written here. Everything is 1/1. By changing these ratios, we can do some really interesting things, looking at harmonic conversion, looking at the various harmonics of the output of the mixer with respect to the input. We will play around with those a little bit later, but it's really helpful to be able to basically do any kind of measurement that you want on a mixer. Now we go back 1 tab. And here is where we do our frequency planning, defining the relationship of the input and output frequencies of the various ports, and of course then defining whether this is a down conversion or an up conversion mixer. Now the instrument does give you some hint down here telling you that these numbers that are entered right now don't make sense. Of course there is a strict relationship between the frequency conversions of any mixer, so you can't just enter any value you want. It wouldn't make logical sense. So it will help you. And this diagram over here gives us more feedback. So let's think about what we want to do. Let's say that I have a down conversion mixer and I'm interested in using it in some kind of a super heterodyne receiver with a certain IF bandwidth, and I want to measure its IF bandwidth, which means that I want to sweep my RF input at a fixed local oscillator and see what happens to the IF. So let's go ahead and do that. So let's say that a local oscillator is fixed and I want to fix that local oscillator to 2 GHz. So I will enter 2 GHz and I want to measure on the upper sideband of the RF and see what happens to the IF input. So let's say I want to say my RF input comes from 2.1 GHz and it goes all the way to the maximum frequency range of the instrument. Now in this situation, I want a down conversion, so I select the negative over here and I can say calculate output, and you can see that it automatically has calculated the output for me and the error is now gone. So if you look at this, it makes sense now. The LO is going to be fixed, 2 GHz, 10 dBm. It's going to sweep the RF input from 2.1 to 8.5, and of course when they mix together you can see 2.1 mixing with 2 on the upper sideband will be 100 MHz, and then 8.5 mixing with 2 is going to be 6.5 GHz, and that's shown over here. And that's it. That's the configuration of the mixer. We're going to apply that. Then the last tab over here is the power tab. It's going to ask us what kind of power do you want me to apply to the RF input. And this is important because the mixer linearity and some of its characteristics are going to be a function of its RF input. Now there's also power coupled on port 2, and it's going to apply 0 dBm on port 2 as well. Now this may seem confusing because if I'm using a down conversion mixer, why do I care about applying a power to the IF port? The IF is my output. But that's because we can also measure the return loss of the IF port, because this is also a network analyzer. Not only that, we can use this to measure the reverse isolation of the instrument. We can find out what happens from IF to RF, the backward conversion. So all of that can be handled in this one setup. And then we have all of this configuration nicely done, but you may think we're done, but not really. We still need to calibrate the instrument. Now, unlike the calibration of a regular network analyzer, there are some additional things we need to worry about, which I will explain. Now, the calibration using an ecal is pretty straightforward. We've done that many times before, and we will do this again in order to calibrate the ports so we can measure S parameters on top of making frequency conversion measurements. Now, it's really nice that Siglent supports other vendors' ecal modules, for example, this Keysight one. Even though they make their own, they still have that external support. Please don't ever change that. That is really helpful. Now, remember that a network analyzer is never measuring absolute values of anything. Network analyzers are always making relative ratio measurements. As a result, the exact power coming out of the port and the exact measured power going into the port is not very critical. Only the relative ratio is important. And if you really want to have very accurate power conversion measurements where you are making absolute measurements like a mixer, you need to do a power cal on top of that. The power cal is simply using a power sensor like this one, and it's going to sweep the frequency and measure the power using this, which is very accurate, and it's going to calibrate its own sources to make sure everything is correct. That's really handy. Again, you can see I'm using a Keysight one because the instrument supports this particular one as well, which is super handy. Again, I hope that they always maintain that. So we're going to have multiple calibration steps, which I will show you in order to be ready for a really accurate mixer measurement. So first we're going to use the ecal connected to port 1 and port 2, which are the RF and IF port of the instrument, giving us S parameters for those two. Simple step. Now back on the instrument itself, under the calibration menu is where the mixer calibration button is located. There's also a button down here called avoid spur. Now this is interesting, and it's a capability of the software of the unit to try and avoid its own internal spurs. Because remember, these frequency converters like mixers are going to create a whole bunch of different intermodulation terms on their own. But then the instrument itself has some inherent ones as well. But because it has a knowledge of its own frequency planning, it can try and get rid of some of those spurs. So let's go ahead and turn that on. And then we're going to click on mixer calibration, and then we're going to enable ecal. So there's multiple steps here to complete. As soon as I select ecal, it's going to give me some instructions on how to connect it. Not very interesting, it's pretty straightforward. And we go over here, it's going to read the coefficients, and then once I click on open here, it's going to ask me where have I connected the ports. So in this case, port 1 is actually connected to port B of the ecal, and the other one is connected to port A. And if I click OK, is going to go through measuring all the open, short, load, and throughs of the ecal. This step is essentially identical to the how you do an S parameter calibration, so there's nothing unusual going on here. Now once that is fully completed and stored in memory, once I click next, now this step is new. This is our power measurement calibration. And here now I have removed the ecal and connected the power sensor directly to port 1. This allows me to power cal port 1 precisely to the measured value of this power sensor and calibrate the transmitter and receiver at every port, which is required for knowing absolute power measurements. And with the connection made, we can go and start the power measurement here. And look at that, it's going through applying a power and measuring essentially the error and correcting for it. This is a very, very small scale, half a dB per step, but after this step, it basically should have no errors at all, and it's going to go through this. It's also simultaneously giving us S11 because it's already done the measurements for that. And it's going to go through this, and I have to do exactly the same thing on port 2. And the final step on now port 2 is going to do basically exactly the same thing. And while it is running, notice how this shape is different than the other one. That's because, of course, the port 1 and port 2 of the instrument are a little bit different from each other, which is the whole point of this calibration. In this case, there's actually some excess power on this port at the beginning of the sweep, and it's going to correct for that. Finally, we can measure our mixer, and this is the mixer that I want to measure. Now this is interestingly an IQ mixer, so it has two IF output ports and an I and a Q, which are quadrature with respect to each other. And I'm interested in comparing the two of them and see how well their amplitude matched. So the LO here comes in on this port, the RF here comes in the middle, and right now I'm measuring the I port, which is connected to port 2. The other port Q is terminated into 50 ohms, so we can switch it later on. Let's see the IF response of this unit. And here are 4 plots representing the characteristics of our mixer. The S21 is the conversion loss of the mixer, the thing that we were interested in when we were losing the mixer as a down conversion. The reverse isolation is the opposite of that, we'll talk about that. S11 is the input match of the RF port, and S22 is the output match of the IF port. And there is so much we can extract by looking at these 4 ports. First of all, the conversion loss of the mixer is around -11, which happens to match almost perfectly with his data sheet. And if you look at low IF frequency, so here, for example, at 2.1 gigahertz or so, that's an IF of 100 megahertz, because our LO is fixed at 2 gigahertz. You can see the conversion gain is flat up to a certain frequency, and then it begins to roll off. So around, let's say, over here or so, we have our 3 dB point. So this mixer at 3.5 gigahertz already is running at an IF of 1.5 gigahertz, and that's basically the bandwidth of the IF port of this mixer, and that's exactly what the datasheet says. And if you look at the bottom one, we see that these shapes are almost exactly the same, and the values are almost exactly the same. This also tells us this is essentially a passive mixer. It's a double balanced mixer using diodes internally, and as a result, it's essentially bidirectional. If you apply an IF signal, you get an RF out, and vice versa. And that's also an expected behavior from this mixer. Now, once you go to really high frequencies at IF, there's some interesting things happen that are no longer symmetric between the two. This is well above the frequency range this mixer is supposed to be used for. But it seems to be some kind of a resonance happening, potentially in the IF or the RF or the LO port. It's not clear. And at some point, it's just going to have a little bit of external gain. But that doesn't really mean anything. We cannot really use this mixer in this point. The S11 and S22 are also some hints about that. S11 is the input matching at the RF port. So you can see that the input matching at the RF port does, reasonably well around -13 or so, all the way up to 3.5 gigahertz, which matches again with its 3 dB bandwidth. So all of these are fairly consistent. The IF port, however, has a return loss much lower, around here. So essentially, they don't really expect you to use this mixer above an IF around 1.1, 1.2 gigahertz. This is for QPSK modulations around 1 to 2 gigawatt, which all lines up exactly as we would expect it. Everything else above here, the return loss is not very good on the various ports. That's because the mixer, again, is not supposed to be used there. But you can see how easily we can get a lot of characteristic, even the reverse isolation at the same time, directly in one setup using one instrument. So now let's use the instrument to figure out the amplitude balance of this IQ down converter, because we should be able to switch the IF port from I to Q and make that measurement. But first, let's store every one of these curves to the memory of the instrument. That way we can easily compare them. So I'm just going to click on every single one of these and then simply put them in memory. Now that they're in memory, I can switch the port to the other one. Okay, so now we are looking at the Q port of the mixer, and you can see the orange line is the original measurement we were making on the I port. And look how similar they are, and that's to be expected, because this mixer is supposed to have better than 1 dB of IQ imbalance across this frequency range. Now we can do one better. We can actually divide these numbers together in linear mode, which would be a subtraction in dB. So in the math here, I can just say divide this for me. And once I divide them, now I'm looking at the dB difference between the two of them. So yeah, it looks really good, as to be expected. Again, this is supposed to be a reasonably good mixer. And here on S11, that's the RF input port. We don't really expect anything to be different between the two of them because we're still measuring the same port. And even here on this port, we expect the Q port to be very similar to the I port in terms of its return loss. There you go. So now if I look at this marker, this number I'm reading here is not the difference, which is the IQ balance. So you can see that the Q is a little bit different by about half a dB or so. Not a big deal. Even in reverse, they're very, very similar. So it meets its specification. And look how easy it is to manipulate the data and very quickly figure out the performance of the mixer. It's also important to note that how we get away from the fundamental frequency operation of the mixer, and the difference between the IQ ports drastically grows. And that also shouldn't surprise us because it's well beyond the frequency of operation. And at this point, the IQ quadrature hybrid, which generates the quadrature signal inside the mixer, is operating well above its frequency range. And of course, it doesn't do what it's supposed to do anymore, and that's going to translate directly to amplitude imbalance of the mixer. So it all makes sense. So far we looked at the frequency response of the mixer, but we know, particularly for a passive mixer, that its conversion gain is going to be a function of the LO power, and we can investigate that using the instrument as well. This time we're going to do a power sweep. Now if I go back into the mixer setup, you can see the mixer setup hasn't really changed. Everything is exactly the same, the ports are the same, but now it's asking me for a sweep on port 3 power. That's our LO power. So we can go from something like minus 10 dBm, even lower, and go from minus 10 dBm to, let's say, plus 15 dBm, let's say at this range. That's 30 millidBm per step because we have a lot of points. Now if I go under the power tab here, it's also asking me for a power range on the other ports, but I don't want to sweep the other port power because I'm only wanting to investigate the effect of the LO power on the conversion gain. So I'm just going to tell it, don't change those, just go from 0 to D0, and the other one is of course also going from 0 to 0. So now it's set up again. Now I have to go back to mixer frequency and make sure these things are entered correctly because right now I still have the error. So let's measure this at a fixed frequency, let's say at the lower frequency part. We can say measure this at a 2.1 gigahertz RF input. Let's leave this here and calculate the LO. So now we're at 100 megahertz. At 100 megahertz IF, we are well within the bandwidth of the mixer. So this is going to isolate the other effects. We're not going to look at frequency response anymore. We're only going to look at the effect of the power. And I can go ahead and look and see what that does. Now we have to be a little bit careful reading this value because if you look at the x-axis, it says that the power starts from 0 and ends at 0. That's because it's referencing the port 1 and port 2 power, which we are not sweeping. We're only sweeping port 3. In fact, if you go into the port power menu here and select port 3, you can see that indeed we are doing that, but it's not showing it, and I could not find a way to change the x-axis to reference port 3 power. So you have to translate that yourself. Left side is minus 15, right side is plus 15. I think there should be at least some way to get the marker to show a different value, but perhaps that is something they can add to the firmware. But if I go all the way over here, you can see when the LO power is high, the conversion gain is back to where it used to be in the previous measurement, because we were doing a 10 dBm LO. So of course the conversion looked really good. But if I lower my LO power and go all the way down here, I'm losing a significant amount of conversion gain. So this characteristic that the conversion gain increases and flattens out up to a certain point is very much like how a mixer should behave, particularly a passive one. Now if I could increase the LO power even more, eventually it would dial back down, which the mixer would enter this horrible nonlinear mode, and then things would break down. The similar in the reverse isolation is about the same, but you can see these transition points are not exactly the same. But the other cool thing to notice is how the return loss actually gets better when the LO power is high, because the S11 and S22 of this particular mixer are designed to operate with a strong LO coming in. They're matched under those nonlinear conditions for the LO port, and that makes sense. And they do get better as the frequency goes up. You can see S22 matches quite a bit better. S1 is around minus 8 or so. Yeah, so here's a very quick, again, another way of measuring the mixer performance, this time as a function of LO power. Now, one thing to keep in mind is that while we did measure the amplitude imbalance between I and Q, we could have measured the phase imbalance also if we had the other mixer measurement license, the vector mixer measurement, because in that technique, you would get the group delay through the mixer, and therefore we'll be able to tell how well the phase matching is. And perhaps if I get that license in the future, we'll be able to try it out, and that will give you the complete characterization of this IQ down converter. Now, because the instrument gives us this interesting frequency multiplication ratios, we can begin to do some unusual things. Let's go ahead and see if we can measure a frequency doubler. So this frequency doubler is supposed to work from around 3 gigahertz to 7 gigahertz or so, and I've connected it between port 1 and port 2. Of course, the frequency doubler is basically a self-mixer, but it doesn't have an LO port, so I've just terminated the LO port of port 3. Let's go and configure the instrument, see if we can get its frequency multiplication conversion loss. So now in our mixer setup, I have the port 1 with a multiplication of 2 over 1, meaning that I'm interested in looking at the second harmonic of the conversion here. But we still have to do something a little bit more clever, because if you go under the mixer frequency, there is no way to enter 0 for LO, so that the signal mixes with itself. I also can't make everything to be variable. Something has to be fixed in this set of combination. So what I've done is that I've set the local oscillator to 10 kilohertz, and I've fixed it. In this situation, 1 gigahertz to 4 gigahertz input translates to 2 gigahertz to 8 gigahertz at the output, because there's a multiplication factor already in there. That multiplication factor, you can see, is written right over here. So now we will run into a little bit of a problem, because this output is not exactly twice the input. But what I can do is I can go over here and change the bandwidth of our IF filter to be wide enough to catch this 10 kilohertz offset, meaning that I'm integrating the power over a 1 megahertz bin, and therefore it doesn't matter that this is not exactly 2 gigahertz. This is the way I found to do this. Perhaps there are other ways, but then maybe they can also adjust the firmware to be able to measure multipliers much more easily. But let's see if this works. One other thing we need to make sure we don't forget doing is to change the power of the port, because in this case I need to put a lot of power from port 1, which is the input of the frequency multiplier, so that second harmonic can be generated, and this part requires about 10 dBm. As you can see, I have adjusted here. If I go back over here, this power no longer matters because the LO port is connected to nothing anyway. So let's see what we have. If I click OK, and check it out, here is our conversion gain. You can see the conversion gain is about minus 12 dB. So I'm losing 12 dB of gain when I'm converting the frequency to twice its value. Now, is this correct? Well, I have the data sheet of the part, and check it out. The conversion loss is between 11 to 15, which is exactly what we are seeing. So it all makes sense. If I go back, you can also see the S11 and the S22 and everything makes sense. And if you look at the reverse isolation, it's sitting well below minus 50. And that also makes sense because the multiplier is not bidirectional. And as a result, you don't expect to see reverse isolation here at all. But in one setup, I'm looking at the conversion across the entire frequency. In fact, this is wider than what the spec says because the spec is a little bit more conservative. So now you may ask, well, what if I want to see my harmonic rejection in exactly the same setup? Well, you can also do that. All I have to do is to change the mixer and not have that multiplier anymore at the output. If I go over here, put this to 1, I go in the mixer frequency and I calculate the output, and you can see now the output is the same as the input essentially, except for the 10 kilohertz offset, which doesn't matter because we have a wide enough IF. And if I apply that and go back, look at that. Now I see that the fundamental rejection, the same frequency at the input, is minus 27. And the difference between those two is my harmonic rejection in total, in dBc. So I had about minus, let's say, 11 or so, and I have minus 27 or so here. Okay, so I'm looking at 15 or 16 dBc. I go back over here, and check it out. That's exactly where it sits. The typical output fundamental tone rejection is between 11 to 18. So it all works out. In one setup, I can measure all of these parameters quite easily. Now let's talk about making some TDR measurements. As I mentioned earlier, there are several ways to do such a thing. Most of time domain based instruments create a sharp pulse or a very sharp rising edge like a step function, and then they measure the response of the channel that way. Or if you have a frequency based instrument like a vector network analyzer, you can get the frequency response of the channel, and from that you can use the duality of the frequency and time relationship and figure out what the step response of the channel is. And from that you can compute things like eye diagram, which can be really helpful. So this is now a software-based solution that sits on top of something like a vector network analyzer. And of course the Siglent instrument has that option as one of the things you can purchase for it. So let's take a look and see how well it can be used to characterize something. Here I have a SATA ISI channel emulator. This is basically a whole bunch of different traces that can be used to measure things like 1.5, 3 gigabit and 6 gigabit per second equivalent channels that are SATA compatible. So you can imagine that if you try to put 6 gigabit per second in a 1.5 gigabit per second channel, you're going to get a ton of ISI. So I want to see if we can characterize this instrument using the network analyzer. We can access the TDR software by going under Math, and if you have the option, selecting the TDR over here and turning it on. And as soon as you do this, a new piece of software takes over the instrument, and a wizard is launched that helps you guide through the setup of the TDR, which is helpful if you've never used this type of TDR on such an instrument before. Now, before we do anything, we have to do some deskew and some loss compensation. Now, the deskew step is particularly important because it brings the phase measurement plane to the edge of the channel so that you're not measuring the cables that you're connecting to the channel. It essentially removes the effect of that. Now, if your cables are low loss, it doesn't matter to remove their losses. But in this case, we're going to do a complete deskew and loss compensation, meaning that it's going to do additional calibration step to figure out the loss of the cable as well. This is going to be a complete calibration step. Now, when we click next, because we do have a 4-port network analyzer, we have the added benefit of being able to select a completely differential channel because it's going to use all the 4 ports and it's going to show us exactly how that should be connected. This is also really important because the majority of backplane channels are going to be differential, and measuring them in differential stimulus is particularly important, which is exactly what's going on here. Now it's going to walk us through various calibration steps. Now, the very first thing it's going to do is going to ask you to leave everything open to the edge of your cables. And that should make sense also because it's trying to figure out the length of those cables, which you can do by measuring the S parameter of each of these ports individually. I've actually already done that. Everything is disconnected. So I can click on deskew. And if you look up here, you can see it's going to go through S11 measurement, then S22 measurements, to S33, and finally S44, which is consistent with being able to remove the cables at the input. After that, it's going to ask for additional steps. And next, we need loads on all the 4 ports. But you don't really have to have 4 individual 50 ohm loads because you can measure these individually, port 1 to port 4 separately, which is what I'm going to do. So port 1 right now is connected. So if I click on that, it's going to measure the return loss, which is going to be well below here. There's minus 20, minus 30, and this is okay. I'm just going to sequentially go through all of them. And we're going to also measure some throughs. That's going to give the loss of the entire setup, and the combination will give the instrument everything it needs to de-embed the setup. And after the calibration, we now simply connect port 1, 2, 3, and 4 to a differential channel on this channel emulator and do some measurement. And with everything connected, there is a lot of information that the instrument now is giving us about the nature of the channel that's being measured. Remember, this is a fully differential measurement. On the top left, we have the impedance. Now, for a differential channel like this, we're expecting 100 ohms. And you can see that it starts at 100 ohms, and right at the border where we're applying our impulse essentially, or a step function, there's a little bit of discontinuity in the impedance. And that's to be expected because we do have some connectors, and we also have the SMA connector that's soldered onto the PCB, and there's going to be a little bit of discontinuity at that point. But everything looks good. Remember, this is as a function of time. At the bottom, we see our step function. After some delay through the channel, it arrives and does have this low-pass filter characteristic to it. That's also to be expected because we are using a 1.5 gigabit per second channel. So it's going to have some low loss, which we will see. The return loss looks reasonably good on both sides, and if you look at the response of the channel itself, it has a very classic 1 over F drop, which is consistent with ohmic and skin effect losses through it. It's a very well behaved channel at least. So now we can go ahead and adjust some of the parameters of the TDR and make sure we get a nice eye diagram emulation of what this channel would be doing. And all the other settings, I'm really not going to change anything in here, but note that I'm applying 500 millivolt stimulus amplitude. You can see the DUT length is automatically calibrated and calculated. Everything else looks nice. You can do some averaging in here. There's some hot TDR, and this is an interesting topic itself. It allows you to avoid some of the spurious that may come from the network analyzer itself. You can run this in this situation. We don't really need it. And then we'll talk about some of these other capabilities of the advanced waveforms. And under the TDR TDD menu, we do have both the frequency domain and time domain options to make essentially any plot that we want. So for example, if I select the S parameter measurement, we're going to get the S parameter domain, which is the primary domain this instrument is actually operating on. If I measure any of the time domain waveforms, it's going to switch to time domain, which is the equivalent conversion back to the time domain measurement. Here we also have control over the DC extrapolation, which I'm letting it do by itself. Sometimes some channels can cause some discontinuity at DC, and it's going to mess up the eye diagram, so you can have some control over that. There's memory, gating, search, and markers, and all kind of other interesting things, which I'm not going to go into too much detail here. One thing I do want to point out is that if you look at the S parameter of this channel, its 3 dB bandwidth is only about 700 megahertz. So no wonder that this channel is only rated at 1.5 gigabit per second. If we go way above that, we're going to get a lot of ISI, which we will see. But let's start with creating an eye diagram at exactly the rated bit rate here and see what it looks like. So let's do some configuration under the eye mask menu. So first thing is asking me what kind of PRBS signal I want to apply. Now generally you want to apply a fairly long PRBS sequence in order for it to have a fairly complex frequency response, so you get a true representation of your ISI and jitter, but it supports many different kinds of lengths. It's sometimes helpful to go back to lower lengths because you can then tell what the problems are and where the transition densities, for example, make a difference. So let's select the highest one over here. Let's get the 500 millivolt be the top level of the eye. Let's make 0 to be minus that. And for data rate, let's do 1.5 gig, which is what this channel is rated on, with a rise time of 100 picosecond, which would be the equivalent input. I think that's it. That's all we really have to do because everything else is already done. And let's do some eye diagram. Let's see how long it takes. It takes about maybe 5 to 10 seconds for us to get this eye. And check it out, it looks beautiful. This is a fairly good eye at 1.5 gigabit per second, which again shouldn't be that surprising because it is rated for this amount. And it's giving us a jitter 30 picosecond. This is essentially entirely from ISI, and all of those parameters are displayed here at the bottom as well. So you can see, the zero crossing is 50%, which is good. It should be. There's no reason it shouldn't be anything other than that. And the jitter RMS is 7.1 picosecond, which is that's why this eye is so open, because the width of the eye is much, much wider than that. So look how easily we got a nice eye diagram at 1.5 gigabit per second. I can also add a mask to this. I've already defined a mask. You can also define your own mask or choose a standard mask. And in this case, if I enable the mask, you can see that it says pass here on the top right. And yep, it's well within the margins of this mask. It looks good. But if I go ahead and now change this to 3 gigabit per second, basically double my data rate, and then draw another mask, now I should expect to see a lot more ISI, and this eye is going to be a lot more closed than it used to be. And look at that, it is indeed a lot more closed, and now we get a fail because it's now violating the mask. I can push that even higher. I can go, let's say, to 5, and at 5 it's going to be, of course, even worse than that, but it's nice to be able to generate eye diagrams pretty quickly. Yeah, it's fairly fast in doing that. Let's see what it looks like at 5. There you go, yeah, it looks really ugly now. It draws this line in the middle, which I don't actually know why that is. It doesn't do that at other baud rates. Maybe it gets really confused when the ISI is really bad. But yeah, it's now completely failing. So let's go back to our 1.5 here again, and then make sure that it does draw the original one correctly again. Here we go, back to the original one. Let's see what it looks like. Yeah, looks good. Back to exactly where it was, and that line is gone. Not sure where that is coming from. Now you can also change the length of the sequence here, and you will see that it will have a major difference. So for example, at 3, where we were having this problem with the eye, I can go ahead and change that to, let's say, a PRBS 5, and you will see a very, very big difference in terms of how the characteristic is. Look at that. You see there's not enough transition density, so we're not getting a really meaningful RMS value of the jitter, but this does help in some scenarios. Now, because we're measuring the S parameters and then calculating the eye diagram, in theory, we should be able to investigate the effect of various equalization techniques directly on the eye by playing with their parameters. And this instrument indeed supports that. If you go under Setup, we do have some advanced waveform section here. If I click on any of these, it brings up a new menu. In this menu, I have a few options. I have the option of doing emphasis. Emphasis is typically done by the transmitter, and it allows you to do precursor and post-cursor pre-emphasis on the eye before they enter the channel. And this is a common technique. All wireline transmitters pretty much these days use that. On the other side, equalization is done typically by the receiver, and this is, in this case, supported by a CTLE, a continuous time linear equalizer, and you can apply some function to compensate for the losses of the channel, boost some of the high frequency content. In advanced wireline systems, all of these are used in combination, and there are advantages and disadvantages to pre-emphasis and equalization. So in this case, we can take advantage of the equalization. There's two other things in this menu. You can actually de-embed various connectors or other things from your channel. This can be helpful if you really want to know only the effect of, for example, traces on a PCB. You don't care about the connectors in this case. You can actually de-embed those. That's helpful. You can enter a file to do that. And you can also add your own jitter. Adding jitter stresses the eye, so you can see what happens in the presence of various types of jitter. We don't need to look at that right now neither. Let's look at the equalization. Now remember that this is all being measured live. So let me move that all the way over here. And this is one of those situations where I think some transparency would actually be helpful, because you can see the traces behind here. So if you remember, we measured that the 3 dB bandwidth of this channel here is around 700 megahertz. So if I add a 0 around the same frequency, I should be able to compensate this channel reasonably well and get a much flatter frequency response. So you can see I have entered my 0 frequency to be around 700 megahertz, and my poles are at 2 and 4 gigahertz. If I go ahead and enable that, look at what happens to the S parameters. Significantly better. Now, this is by no means the optimum value for the CTLE. You can tell that because there is some overshoot in the step response. But this is still going to improve the eye a lot, I believe. Let's try it out. So now that it is in there, we can go back in the eye and we can generate a new one based on those parameters, and let's see what happens. Let's see if it's a lot better than it used to be. Look at that. This looks beautiful. This is now a 3 gigabit per second eye. It's not completely open. It does have some overshoot. You can see that. So perhaps it's a little bit too much, but it passes the mask now again. So it tells me that if I could implement that CTLE, I will be able to completely open this eye without any issues. So now I suspect that I might even be able to do 5 gigabit per second through this channel. Well, at least it's going to be close. Let's see what happens at 5 gig here. Although I did add that pole at 4 gigahertz, but let's see. Yeah, look at that. There's some double edging going on in here, but the eye is still open, and it does this line in the middle, which I still don't know why it does that. But look, even at 5 gigabit per second, it works. The reason it says it's failing is because of this line. I think there's something going on in that calculation. But yeah, you can see how important these functions actually are. We can dig into this much more and add preemphasis and everything else. One other thing I wanted to note is that it does give you the option to look at what the eye would look like if you apply preemphasis to it, so you know what kind of eye you're generating and putting into your channel. There's a lot of advanced functions in here. By the way, this is by no means the end. They can develop a lot more stuff if they want. They can do better equalization, more flexible equalization, and even do some routines to calculate the equalization coefficients automatically if they want to. There's a lot of possibilities here. And there you have it. I hope you enjoyed this second part review of the Siglent SNA5000 series network analyzer. And there are still more features that I want to take a look at in future videos, things like the gain compression option and the spectrum analyzer option. But check this out. Now, this is the Siglent SNA5000 series network analyzer, the latest high-performance platform. This particular one is a 4-channel 13.5 GHz model, but they go all the way to 26.5 GHz. Now, this is competing with some of the biggest players in the world, so the teardown, review, and analysis of it should be super interesting. So make sure you subscribe to the channel if you haven't done so already, so you don't miss it. And as always, let me know if you have any comments or questions in the comment section. I'll see you next time.